Now we get to do vectors. Again. But what we did was not in vain. Almost everything we worked on will be imported, but we have to think very carefully about our basic definition of vectors. So the first thing I want to remind you is that there's not going to be any notion of a position vector. We're not going to regard the coordinates on the manifold as a position vector. So no, this is gone. We were able to do that when we insisted that the space-time was R4 and we were in Cartesian coordinates, Lorentz frame. We had a notion of position vectors, taking the Cartesian components of a vector in space. They naturally add like vectors do in vector spaces, and it's all very useful. That's gone. There's no analog of Cartesian coordinates, for example, on the surface of a sphere, or in general on any manifold. So we're not going to have that. But we're going to keep the idea of this thing, some dx mu d lambda, tangent to a curve. So this thing should still be a vector, more like a velocity vector, a little local infinitesimal displacement. So if I imagine the curve is time-like, it looks something like this, and the picture is, there's your little vector t, which previously we wrote in components as dx mu dt, and we had this e lower parentheses mu hat. Remember that? Not t, lambda is the parameter. And in special relativity, we argued this was a vector because we already had position vectors from the coordinates, and we introduced things this way. In curved space-time, we're going to need an independent definition of a vector. And in contrast to the definition of manifold, which is very physical and intuitive, the definition of a vector that's most convenient is not at all intuitive. You get used to it because the notation is so slick, and it lets you introduce vectors without working too hard, but it's not so physical feeling. And here's the trick. What we do is we think about the question of how does a function f change along a curve. Some function f of x mu change along this curve. Okay, well, we can compute df d lambda, right? That, by definition, what we mean by that is d by d lambda of the function evaluated on x mu of lambda. This we can do without calling x mu a vector. We won't do that, but x mu of lambda is a thing. It's the coordinates as a function of parameter. We can plug that into our function, which takes a slot for coordinates. And now we have an ordinary function of lambda. We can take the ordinary derivative. Okay. Now this here, now we can use the chain rule. So this is going to be partial f, partial x mu, dx mu, d lambda. And you can see now that here, that the thing that was the components of the tangent vector in special relativity has appeared. We would really like to call this blue thing t mu, the components of the tangent vector. And as motivation for the definition, let's kind of peel off the f. Let's say that f led us to thinking about how this thing we want to be a vector might appear. But let's just take the leap and say we could write the following. D by d lambda equals dx mu d lambda d by dx mu. Okay, this is just something I'm choosing to write. I'm going to use this as part of the definition, but it's a natural thing. You could imagine thinking of the action of this tangent vector we're trying to define on a function as an operator d by d lambda that's ready for the function to be stuck in. And then you just stick the function in on both sides, and you immediately get this. But then what we do to start turning this into an actual definition is we compare to special relativity, where these things here were our basis vectors. And we say this should be a basis vector, an abstract basis vector. And we say this thing then should be the tangent vector, abstract tangent vector. That was what we had called t before. And then it will work out just like it did before. These dx mu d lambda, this will be t mu, the components in this basis. So what I've done here is I've actually defined an abstract vector as a differential operator, d by d lambda, the operator that takes functions f and returns this thing on the right-hand side. So that's a directional derivative operator. We could define it abstractly as a map from functions on the manifold to numbers that's linear and satisfies the Leibniz rule. And so if I kind of wanted to just cold-hearted give you the definition of a vector, I would say a vector at a point P is an operator that takes functions on the manifold, returns numbers, and it's linear and satisfies the Leibniz rule. Okay, that doesn't sound very much like a vector to all of you, I would assume, but hopefully what I wrote here helps make clear why it really is behaving exactly like a vector did in special relativity. Yes?
So is it like, how literal are we with calling these like basis vectors? Like it's like these are basis vectors as in they will behave exactly as basis vectors do, and we're just going to use them that way?
If you want to do it the cold-hearted way, which takes a little more work too, which is one of the reasons I don't, you first define a vector at a point P as a map that's linear and satisfies the Leibniz rule. Then you prove that given a coordinate system x mu, these particular ones, the partial derivatives, are A, indeed vectors, and B, form a vector space of dimension n, where n is the dimension of the manifold. And they're linearly independent, that's obvious. So they really do form a basis. So Carroll in the book kind of hints around this. If you go read Wald, which is the more straightforward mathematical approach, he just does exactly what I said.
So,
Yeah.
like the vector acts on functions, not position vectors, right?
There are no position vectors.
Because there are no position.
Yeah. So
So like, how does the fact that we're working in curved space have to do with why we have?
well, previously we defined a vector by starting with the Cartesian coordinates of the manifold as our vector. And we don't have those preferred coordinates anymore. There's no notion of Lorentz frames. Right, a Lorentz frame, there were various, I forget how we actually introduced it. You could say a Lorentz frame is something that leaves the metric invariant and introduce Lorentz transformations. And then we demanded that our abstract vector, so we took our position vectors, our definition, we demanded that our abstract vector could be expressed using an equation of the same form in different Lorentz frames. And we got a tensor transformation law and all that. So that all started with defining x mu itself, the coordinates, as a vector. We can't do that anymore. What would you choose on a sphere? Theta and phi? Like, that's not how vectors behave. So we need something else. And this is what everyone has settled on as the most natural and useful, even though it's a little mystifying at first. Okay? So you can ask questions now or later. This is just something you end up figuring out how to use and accepting. But this does give a notion of an infinitesimal displacement on the manifold in a certain direction. That's now represented. So the idea of moving a little bit in the x direction is now represented by a vector, which is a partial derivative operator. So we say things like the vector d by dx. Right? This thing is now a vector.